Hi, this tutorial is to introduce you to NDSolve, Mathematica's built-in integrator. To do this, we're going to model the motion of Usain Bolt, the world's fastest sprinter, as he runs the 100-meter dash. In this model, we will include the average net force that Usain is able to sustain throughout his run and the effects of air resistance. In our model, we will use the equation for quadratic or turbulent drag to model the air resistance. To get started, we need first to open a new notebook in Mathematica, either by clicking File, then New Notebook, or using Command N. I've done this already. This notebook will be empty. First, we'll need to define a few constants. In Mathematica, the names of functions and known variables start with capital letters. If you want to define your own constants, I'd suggest using only lowercase letters. First, we'll define Usain Bolt's mass. Wikipedia estimates his mass at 94 kilograms. We'll simply type m equals 94. Then we'll hit return. Notice that Mathematica hasn't actually done anything. By hitting return, all we did was kick down to the next line. I'm doing this because I want to keep all of our constants together in one section. Next, we'll define the average net force that Usain can sustain. Let's estimate this as roughly 300 newtons. So we'll type F equals 300. And again, we'll hit return. Finally, we'll define Usain Bolt's drag coefficient. Usain is an extended object, so this value could be quite large. Let's estimate it at about 1.7. So we'll type C equal 1.7. Now this time, we'll hit Shift and return. This tells Mathematica to execute all these lines. You'll see that Mathematica has returned the values that you entered. This is its way of confirming that it has accepted what you've entered. Now that we've set up our constants, we're ready to use NDSolve to numerically integrate the equation of motion for Usain Bolt. This equation includes the constant average net force that Usain is able to sustain and our model for turbulent or quadratic air drag. I'm going to type this equation so you know what it looks like, but then I'm going to change it a bit to put it in a format that NDSolve understands. The net force acting on Usain Bolt at any time is just F, the force he can sustain, minus the air drag. Unfortunately, NDSolve doesn't understand this intuitive format. To solve for his position as a function of time, we have to rewrite this equation as a differential equation for x, his position along the track. To start, we'll first delete what we've typed here, and then we'll type NDSolve, open square bracket, open curly bracket. In the first set of curly brackets, we will type our differential equation for x and any initial or boundary conditions for the problem. Because this equation is going to be second order, we will need two conditions to find the arbitrary integration constants. In our case, we will use Usain Bolt's initial position and velocity. To continue, we type the differential equation for x. X prime prime of t equals f divided by m minus c divided by m times x prime of t squared. We will separate this differential equation from our initial conditions by a comma. Let's assume that Usain starts from x equals 0 with no velocity. So we type x at 0 equals 0 and x prime of 0 equals 0. These are all the equations that we need to fully specify our problem. So we close this set of functions with a curly bracket. We now have to tell NDSolve which variable is the independent one. In our case, it's x. So we'll type comma x. Finally, we have to tell NDSolve over what interval to solve our problem. That is, where to start and stop integrating. Because this is going to be a range of values, we'll use the curly bracket notation again. In this case, we want to integrate from t equals 0 to 10 seconds. We will close the whole NDSolve call with a square bracket. We will tell Mathematica to integrate by typing shift return. Notice that the output isn't very helpful. Mathematica has created an interpolating function. To visualize this result, we're going to plot the function x of t. However, because the interpolating function was numerically determined, Mathematica requires some additional syntax to inform the plot function of this. The first thing we have to do is store the solution of the differential equation. So we'll go back to the NDSolve line and type SOL equals NDSolve, etc. Then we'll type shift return again, and now it's been stored in SOL. You should always get in the habit of doing this, because if you're going to be plotting, you're going to need to store the solution. Now we will call the plot function and add a little bit of information that Mathematica needs to plot the result of a numerical integration. So we type plot, open bracket, evaluate, open bracket, x of t, close bracket, / dot SOL. This convoluted function call tells Mathematica that x of t is the result of a numerical integration and needs to be evaluated at each t. The final piece is giving plot the range over which to plot the function x of t. So we type, as we did earlier when we needed a range, comma, curly bracket, t, comma, 0, comma, 10, close curly bracket. That gives the range over which to plot the function. Now we'll close it with a square bracket and hit shift return, and you should get a nice plot. The vertical axis here is the position, and the horizontal axis is the time. Let's say instead that you wanted to plot the velocity as a function of time. And that's really simple now that we've already plotted x of t. We'll just copy the line that we had before and paste it below. The only change we need to make is to put a prime on x. We'll hit shift return, and we see Usain Bolt's velocity is a function of time. Here, the vertical axis is the velocity and the horizontal axis is the time. So that's how to solve a differential equation using NDSolve and plot the resulting solutions. One last thing you might want to do on your homework is to plot the position as a function of velocity. This is called a parametric plot. This time, I'm just going to type the commands, and you can look at the notebook that I've posted to see the details. We'll just hit shift return, and we see the velocity on the horizontal axis and the position on the vertical axis. This concludes the video tutorial on using NDSolve.